Hi everyone, welcome to today's cyber seminar. We'll go ahead and get started in just a few minutes. Hi everyone, welcome to the Fall 2019 Cyber Seminar Series. Just a few things before we begin. Please remember that if you have any questions, to type them into the questions box found on your GoToWebinar control panel. And as always, we will take questions after the lecture has concluded. So with that, I'll go ahead and hand it off to our host, Imad Habib, who will introduce our speaker today.
Yeah, good morning or good afternoon, and thank you for joining us on this third episode of the Cyber Seminar. We have an exciting topic today with a focus on hydrology education at the introductory undergraduate. Interesting for us to hear about how our efforts for advancing hydrology education play out at the very introductory level courses. Before we get started, I would like to introduce our speaker. Dr. Cory is an associate professor of science education in the School of Natural Resources and College of Education and Human Sciences at the University of Nebraska. He is also the director of the National Collaborative for Research on Food, Energy, and Water Education, and the coordinator of the IANR Science Literacy Initiative. His background is in environmental science and science education, and he is engaged in several research and projects and teaching about water systems across K through 12 and post-secondary settings. He leads several projects funded by NSF and USDA NIFA. And in 2014, he was awarded the Early Career Research Award by the National Association for Research in Science Teaching. And he's also a core Fulbright US Scholar. So I'll turn it back to Cory to hear his presentation.
Perfect. Thanks, Imad. I'm going to start the process of showing my screen here and just make sure everybody can see my presentation. Is that visible to everyone?
Yes.
Yep, we can see you.
Perfect. All right, well, as Imad said, my name is Cory Forbes. I'm associate professor here at UNL, and it's sort of a recent, I guess, addition to the CUAHSI, education and outreach committee, and some of the broader education and outreach efforts in the community. It was really nice to be asked to speak on some of the work we've been involved with over the last, I guess, 3+ years at this point. Specifically with the work I'm going to talk about today, which is part of a sort of broader focus on water education that my team has pursued over the last 8 years at this point. So without further ado, I'll jump right in and try to provide a little background here on some of this. So the rationale for this work is probably not mysterious to anyone. We know that the water systems of today and today's most pressing challenges are associated with both the human and natural dimensions of water systems. I think within sort of the broader water science and hydrological community, this has become more of a focus over time. And there's little doubt that certainly water is a key topic and a key issue in really any discussions today about natural resource management, policy, and things of that nature. So the challenge from a natural resource perspective is to continue to be able to provide water for all of its human uses in reasonable quantities and quality moving on into the future. So specifically within education, obviously water is an important topic and one that's included in science standards for teaching and learning, whether at the K-12 level or the post-secondary level, particularly with undergraduate education. There's been a fair amount of research over the years that's illustrated some of the misconceptions and gaps in understanding that students have about core concepts in the water sciences, which could be the topic of an entire presentation onto itself. But suffice it to say, there's a fair amount of work that we have to do yet as educators to try to prepare the next generation of both citizens as well as water scientists for both studying and understanding the nature of water systems today. There's another study here by the American Museum of Natural History that's over 10 years old at this point that also has pinpointed some of these same misconceptions amongst the American public. So certainly the water science community has responded to these challenges in sort of the educational realm with innovative approaches to undergraduate water education for both water science majors and non-majors. So there's a lot of really interesting and innovative stuff that's happening in undergraduate education, for a variety of different undergraduate populations. So things like collaborative assessments, technology-enhanced field work, obviously authentic laboratory experiences, but increasingly also putting modeling and visualization tools into the hands of undergraduate students to give them a feel for sort of the authentic work that water scientists often do, and sort of empowering them to investigate and explore water-related topics at arguably a much more sophisticated level than you could do without these kinds of resources. So this is where our work sort of fits in. We have, over the last 3 years, developed and implemented and revised a new interdisciplinary undergraduate water course called Water and Society. It's really targeted towards more intro level or lower level undergraduate students, both STEM majors and non-majors. The course has a couple of different sort of core foci, one of those obviously being the core hydrology content that the standards and others would argue that your average undergraduate student should learn over time. The course is reflective of tenets of effective undergraduate STEM instruction, including a variety of active learning strategies. We have a very nice class size that allows us to do a fair amount of interactive work in the course. We also utilize undergraduate learning assistants to support instruction as part of the course. There's a focus in the course on science communication. So students have a project where they develop infographics that are meant to be, communication tools targeting a broad audience that is at least partially based on some of the investigations that they do during the course. And increasingly over time, we've used a variety of computer-based modeling and visualization tools, which I'll talk more about these here in a little bit in the context of some of the assignments and the research. And then the last part is really trying to ground the course in real-world scenarios and contemporary water-related issues that are hopefully both engaging and motivating for students to want to actually explore and learn more about. So this work has largely been funded by an NSF-IU's grant, Fostering Undergraduate Students' Disciplinary Learning and Water Literacy. Obviously, as I mentioned before, a big focus of this work is the course itself, but I've been fortunate enough to work with an interdisciplinary team of a hydrogeophysicist and an economics professor to sort of try to address both the scientific and social science dimensions of the water issues that we focus on in the class. We've had a number of graduate student assistants who serve as both teaching assistants in the course, but also research assistants for some of the course-based research that we do. Also undergraduate researchers and learning assistants. The course is situated in a food, energy, and water and society undergraduate minor that's offered here through the College of Agriculture and Natural Resource Sciences at UNL, and connects to a variety of other sort of institutional initiatives. So in a lot of ways, both institutionally speaking and obviously from the NSF's perspective, this was sort of the right thing at the right time, but I think drew a lot of attention from folks. So here's the overarching project logic model. I'm not going to go into a lot of the detail here, but some of the course elements, well, I guess first the project goals. Obviously a primary goal of this work has been to support undergraduate students learning about water systems and specifically their ability to engage in science-informed analysis and decision-making of these broader water-related issues. But then the second and equally important part is actually conducting discipline-based education research to understand, how they reason about these water systems and how various aspects of the course and instruction are hopefully helping them do that better. So the course itself is defined by a series of sort of key things. One of these is this structured decision-making tasks, which are a key part of each of those scenario-based assignments that I mentioned before. Students are asked to sort of adhere to a semi-structured process of decision-making, which asks them to both sort of mobilize the science behind the issue, as well as some of the non-scientific dimensions of the issue to ultimately put forward a decision or a sort of a policy recommendation about the issues that we study. So this is at this point a relatively mature work. We've presented and published on a fair amount of this work over the last 3 years. And so my goal in the presentation today is really just to sort of highlight some of the empirical findings and how they're informing our work moving forward, as this is an area that we would like to continue working in and are actively trying to do so. So the course objectives are twofold and reflect kind of some of the things I've already talked about. So obviously we want students to learn about fundamental concepts in the water sciences related to various aspects of water systems and scientific practices as well. But the second part of this is this sort of decision-making piece, analyzing some of the non-scientific dimensions of these systems and ultimately making decisions about those. And these course goals align with two UNL general education requirements that the course is approved for. One of those, ACE-4, focuses more on the science piece, and the other one, ACE-8, focuses more on some of these ethical principles around stewardship and civics and sustainability and so on and so forth. So this is a course that students from across the university can take to meet one or more of these gen ed requirements if they elect to do so. So what kind of things do students do in the course? Well, they as I mentioned before, they use computer-based models and simulations. We also engage with these sort of broader socio-hydrologic issues that are, relevant to today. We do try to showcase expertise from various stakeholders or contributors related to water science. So not just other water scientists, but also folks who are involved in communications and industry experts. Here in Nebraska, not surprisingly, for example, we have a lot of, or one of, if not the most premier irrigation companies in the world. And so they always have a lot of interesting stuff to share with students about irrigation technology and how that's used in agricultural production. Structured decision-making frameworks. We also do some site visits here at the university, as well as with municipal water facilities. And we actually have a really interesting water facility on one of our campuses that does a lot of water recycling. Work in small group teams to conduct some research. And then one of the things that students have been allowed to do, or afforded the opportunity to do, is present their infographics at the Water for Food Global Conference, which is typically held here in Lincoln as part of the Dougherty Water for Food Institute, which brings in hundreds of international scholars and water resource managers who are interested in what the students are working on. So that's been a really unique experience for them. So here's just some nice pictures of students working in class. One of our field trips to some of the stormwater management resource infrastructure sites on East Campus, and the one on the right there is students presenting some of their work at the Water for Food Conference. So I think in general the students get to do some pretty cool stuff, and the feedback that we've received from students is that they enjoy and appreciate the varied kinds of opportunities for learning and sharing what they've learned with others. So who are the students in this class? Just give you kind of a quick overview. For the most part, we've seen a relatively even split between male and female students in the course, which is perhaps a bit surprising if the majority of them are STEM majors. This is sort of the distribution of their sort of grade level or year in their undergraduate program. So we have tended to get slightly more advanced students than we were initially anticipating, and that has varied a bit over time. So we tend to get a lot of students that are sort of in that middle part of their undergraduate program, and I think there's totally valid reasons for that, and it's actually quite good because the students in the course, by and large, have had some, at least 1 year of undergraduate work under their belts and kind of know the drill and are well positioned to sort of benefit from the course experience. And this actually surprised me a little bit because we've felt like we had a lot more non-STEM majors in the course than this information would suggest. But it does suggest that the majority of our students, especially over time, have been STEM majors from a variety of STEM-focused programs at the university. UNL has a very distributed water science program. We do have an official undergraduate water science program, but it's fairly small, and a lot of students do a lot of stuff with water and a lot of different programs and engineering and other colleges as well. So, bringing all those students together in a class like this is really interesting because they're bringing a lot of different programmatic perspectives, I guess, to bear on the course. So to design the course, we've engaged in a pretty purposeful process of construct-centered design, where we use sort of predetermined learning performances or learning outcomes for students to guide the development of the course activities. And then over time, as we've engaged in research in the course, we use that knowledge gained from that research to make revisions and changes to the course. One of the big things we've done especially over the first couple years, was go from a much more of a traditional face-to-face model to more of a hybrid model, where a lot of our sort of lecture materials and background information and content is in an online format where students are able to access that ahead of class. And that really frees up our class periods to do a lot more targeted, discussion and interactive class activities that sort of reinforce those topics that are the focus of the lectures and background information. So I mentioned that one of the major foci of the class is this, structured decision making, and this is kind of our conceptual framework for what that looks like. It's leverages perspectives from the decision sciences and other uses of structured decision making as a process. And what we try to do is actually help students learn the process of structured decision making to a certain degree to actually work through these challenging water-related issues at various grain sizes to try to arrive at reasonable proposed solutions to them. And obviously one of the things that students really learn from this is that there really never is a right answer. It's all about trade-offs and whose priorities get prioritized most over other priorities that they may experience. And so that's an interesting process for students to really work through that repeatedly throughout the semester. They have multiple opportunities to do this. So in terms of project research, this is based in sort of a design-based empirical research model where the research is firmly embedded in the instructional design process, and the two sort of feed into one another in a reciprocal manner. It's also aligned with guidance from NSF and U.S. Department of Education on what education research should look like at various levels. And in our case, this was a fairly early stage project where we were just trying to figure out things that would work for students and how to design this course in an effective way that would give them a meaningful learning experience. So in terms of the data that we collect, we've pursued a fairly consistent approach where when the course is offered every year in the spring semester, we collect data basically as part of the course offering. So this includes an assessment that students complete, sort of a concept inventory at the beginning and end of the semester, which gives us a measure of their understanding of core water science concepts and how that may change over the course of the semester. There's also a systems thinking assessment, which is a very quick Likert scale instrument that's based on others have developed and published. That gives us a quick measure of their systems thinking. There's a series of decision-making tasks and assignments that are associated with those bigger scenario-based assignments in the course that I mentioned before. We also conduct student interviews with subsamples of students around particularly these decision-making assignments to try to understand more deeply how they're reasoning about some of these issues at sort of critical points in that decision-making process. We also video record most of the class periods, if not all of them, to provide a record of observation of instruction. And then, of course, we collect general demographic information about the students, some of which you just saw a minute ago, just to try to track on who the students are and whether any of those variables have any relation to the outcomes that we see. So I'll just talk through some of the results from the course. As I mentioned before, the course has been offered 3 times at this point. We're preparing to offer again here this coming spring semester. One of the positives that we've seen very consistently over the last 3 years is that students do develop more robust understanding of core disciplinary concepts during the course, which is good. And the students that tend to benefit or gain, student gains are associated with essentially where they started at the beginning of the semester, which tells us that pre-test scores are going to probably tell us something about where students are going to end up later in the course as well. Now, one of the interesting things that we've seen is, obviously at this, with the sample size, our groups of students don't all start and end at exactly the same points. But one of the things that we've seen over time is that, even if the groups of students that we're working with are starting at different levels of conceptual understanding at the beginning of the semester, they do end up at roughly an equivalent place by the end of the semester, which is good. So students, groups of students that have lower pretest scores are making greater gains over the course of the semester compared to other students in other years that may have started with higher or greater levels of understanding at the beginning of the semester. So we also take that as a positive, that the students or the course kind of helps get students to a fairly defined set level of conceptual understanding by the end of the course, regardless of where they're really starting from. So the scenario-based assignments that I mentioned before are a really big focus of our data collection and our research. Like I mentioned, these are based in contemporary real-world water issues. So just to highlight some of these, I don't know if any of you are familiar with NCORE work in Nebraska, but this all has to do with the Republican River, which is in the southern part of the state, and a accord between Nebraska, Kansas, and some of the other states that share the Republican River Basin about how much surface flow each state should receive. And there was a huge federal lawsuit that made it all the way to the Supreme Court, where Kansas had sued Nebraska for basically not getting its fair share of the water. And this is a semi-arid area that, of course, has relatively limited surface water resources to begin with. And so Nebraska's solution to this was to actually shut down a lot of center pivot irrigation and redirect that groundwater to the surface and into the Republican River Basin to essentially ensure that the state of Kansas receives its allocated amount of surface water from the Republican River. This is something that a lot of our students actually are familiar with because many of them are from Nebraska, so it's an interesting discussion. Another one of these has to do with the Raccoon River Basin in the city of Des Moines, which many of you are probably familiar with the lawsuit that the city brought against the surrounding counties over nitrate levels in the water each growing season, which cost the city on average, I think it was something like $7,000 to $10,000 a day to specially treat the water for municipal use. That lawsuit didn't carry forward, but this is a big focus or a big issue that we talk about in the class as an interesting policy discussion about ultimately who should be responsible for water quality, and who should be, who has to own sort of the consequences of the way we use water. And then another big issue or a big topic has been the Keystone XL pipeline, which is very Nebraska relevant here again. And students talk about, or we explore the potential consequences of a spill, which is one of the main, sort of arguments against the pipeline being built in Nebraska. So each of these has a computer-based model associated with it. And like I said before, ultimately students are asked to sort of pose a policy decision or solution that would address the issue at hand. So just to highlight a couple of these tools that we use, one of them is called the Hydrologic Challenge. This is actually developed by some of our one of our nonprofit partners, the Groundwater Foundation, used for actually Science Olympiad with upper level high school kids, but we've used it with these undergraduate students as well, which has been really interesting. And this is one that allows you to really simulate contaminant flow, and if there is a spill, how this might influence groundwater and water quality at various locations. And one of the nice things about these tools is that they're all based on authentic hydrologic data, primarily from the state of Nebraska. So students get a feel that this is really authentic stuff that they can explore and look at, in a realistic way, what might happen in these different kinds of scenarios. Another one we use, which was developed by my colleague here at UNL and one of the co-PIs on the NSF grant, Trenton Franz, is a water balance model, which again is based on Nebraska data. So students are able to sort of explore the potential impact of climate conditions and water resource use on groundwater levels and other sorts of variables. This was a tool that was developed very quickly and in a sort of an ad hoc manner, and we're looking to sort of build this out in a more substantial way in the future. But one of the things that students really like about it is it allows them to explore Nebraska, which basically spans 4 separate climate zones, and what the implications, for example, of climate variability and climate change would likely be on groundwater over long periods of time, which, as most of you are probably familiar, groundwater is essential and fundamental to the entire economy of Nebraska through agriculture. So very important topic. Students are pretty interested in it, and the tool is relatively straightforward and easy to use. And then thirdly, Imad will be very familiar with this one. We're starting this year trying to incorporate HydroViz into the course as another one of the modeling tools that we use, and developing a new module that will allow students to look at, sort of energy water nexus issues, specifically in the state of Nebraska, that kind of align with these other scenario-based modules that they already experienced. So we're excited for this, and this is a piece that's in the works as we speak. So we've done some research on the water balance model assignment, and specifically focused on students' model-based reasoning, or how they use the model to really investigate issues related to groundwater. And one of the things we found is that, for example, students are much more comfortable and able to use the models to actually explore the issue than to turn around and really evaluate the model and what it does and what it allows the user to do in a substantial way. Though we did see gains in these model evaluation scores between year 1 and year 2, which I mentioned before is when we kind of went to the more of a hybrid model of the course. And so, our working hypothesis is that students are benefiting from more collaboration and more time to work directly with the model instead of sort of sitting and listening to us talk about it or related concepts. So there's a lot of qualitative findings that go with this. This is actually a paper that my grad student Diane Lally just published actually like a month ago. So I'm happy to share that if anyone's interested. But we see a lot of the ways in which students, interpret some of the patterns related to groundwater and variables that affect it over time. But as we saw, these patterns remain fairly consistent between the first 2 years that we used the assignment. But some of the things that changed were related to model evaluation, where students were able to sort of be more critical of the model over time and what it did and didn't allow them to do. So for example, in terms of the complexity of the water balance model, a lot of students in the second year, thought the model wasn't complex enough, it didn't provide enough detail, and didn't really allow them to do all the things they wished they could have done to address the issue that we were discussing. In terms of generalizability, students here again looked at outputs really more critically based on how generalizable they were, as compared to sort of year 1 where they did that much less, which was good. And then in terms of the specificity, students thought that one thing the model did well was give them information that was precise, and I think this has a lot to do with the fact that it was based on authentic data that they knew they were using, and not so much on just the user functionality of the model over time. So, I think what we're seeing is that students are becoming more sophisticated users of the model, not so much focused on just the technical aspects of the model itself, but ultimately like how the model helps them answer questions and make predictions and actually investigate the specific phenomenon or topic that they're looking at. So another big piece we've worked on has focused directly on this sort of notion of their students' socio-scientific reasoning about the water issues that we study. A lot of this I've already said, but basically the assignment based on the Raccoon River occurs as part of the final exam, where students respond to a series of questions that are kind of embedded in this theoretical framework for socio-scientific reasoning. And this provides us with sort of a measure of how students are able to reason about these issues not just the scientific aspects of them, but sort of the issues holistically. And this has a series of 5 underlying dimensions. For example, the fact that these socio-scientific issues are complex and they involve a lot of different parts. That inquiry is a critical part of understanding them, and that they involve a lot of different stakeholders and different kinds of information to study them effectively, and that this sort of notion of what science can and cannot do in terms of ultimately helping people solve these problems and address them over time. So this table kind of gives a quick overview of where students' mean scores were for these different elements of socio-scientific reasoning. One of the things they're more comfortable and able to do is sort of take the perspective of various stakeholders who are involved in these issues, whether they're farmers or agricultural producers, whether they're city residents, policy leaders. They're able to sort of recognize the perspectives and priorities that each of those groups is sort of bringing to the table. One of the areas they struggle most with, however, is sort of this notion of skepticism, that science isn't sort of an ultimate answer to everything, and we have to sort of look at these issues with a critical eye from a variety of perspectives, right? And it's what we do with scientific information ultimately that is important, not just the information unto itself. So here are just some qualitative examples, related to skepticism. For example, there's sort of this notion here that the funding and support for the work of the scientists might have a role in the findings that they ultimately produce. So this notion of being skeptical about who's supporting and funding this research that might ultimately inform policy is an important part of that discussion. And this is the sort of a closer look at perspective taking. So not just who the stakeholders are, but what their position against a given course of action might be, and why they might have those, hold those positions essentially. So, some of the rationales will be scientific in nature, but some of them will be economic, for example, obviously because that economics drives a lot of what we are talking about in a lot of these scenarios. So this is a really important work that kind of helps us understand how students reason about not just the scientific dimensions of these issues, but sort of the broader issues and all of their other complex elements, essentially. So last but not least, we've looked at student systems thinking. So also in conjunction with the Raccoon River assignment or task, students actually draw sort of a diagrammatic model of what they envision this system, this socio-hydrologic system to entail, and basically author a news release, another form of scientific communication about the issue and ultimately what's going on. So there's a couple different sort of conceptual frameworks that underlie this, both in terms of systems thinking that sort of highlight these different dimensions of what their systems thinking might look like about this issue. Just to give you a quick overview of some findings, one of the things we consistently find is that students are most capable of identifying what the elements of the systems are. So like if you highlight the different stakeholders and policies and phenomenon that are at play, like students can identify what those are and at least get them into some kind of a representation of the system that they develop. They're a little bit less comfortable with identifying what the mechanisms are, the sort of processes that drive relationships between these systems, and struggle more with some of the phenomenon and patterns that are evident in the system. Of course, one of the things that we find is students that generally provide more evidence of any one of these also provide more evidence of the other ones. So that's probably not terribly surprising, but this is also very consistent with other research only, that focuses only on natural systems. So like you would expect to see sort of the same trends with students who are basically just looking at sort of a natural water system as opposed to one that includes its human dimensions as well. So that's kind of interesting that we see similar patterns in both of those kinds of tasks or activities. Just in terms of those categories from below, we see that students are again most capable of identifying what the problem is and figuring out why it's a problem. They're a little less comfortable with some of these other aspects of it, of figuring out what the stakeholders are and unintended consequences, and some of the other these are really relational pieces of the system that I think this dovetails nicely with some of the work from the previous slide, which shows that some of those relationships are more challenging for them to conceptualize and articulate. So next steps, what are we doing with this? So the work we've done over the last number of years really wasn't originally intended to focus on the modeling piece. It was primarily focused on supporting students reasoning, socio-scientific reasoning and decision making about the water issues. But one of the things that we really discovered is that it's hard to mobilize the evidence that students need to engage in that decision-making process without the sort of tools that allow them to effectively do so. The alternative is for them to sort of pour through, research material and try to come up with all this raw data and stuff on their own, which is just probably not a reasonable expectation for your average, sort of introductory undergraduate student. And so what the models really do is give students an easy way to access that data that allows them to generate output that is immediately relevant to the broader sort of decision-making process. And so what we're trying to do as we move forward is really incorporate these two critical sort of pieces, integrate them into an overall conceptual framework that we can use to really support students' model-based reasoning about and decision-making about these socio-hydrologic issues. So as we kind of get to the conclusion here, I want to mention that the work we've been involved with is sort of loosely connected to this new emerging community focused on education and education research in the food, energy, water nexus. It's an exciting space that's drawing on a lot of people like myself and probably like many of you who are involved in education or are studying or evaluating educational programming that has some connection to the food, energy, water nexus. So I wanted to at least mention this because I think for folks who are doing that work, this is going to be a really engaging space to sort of be working in over time. And this RCN for NCFU has just got started in the last month, and this is a great time to hop on board if you may be interested. And I'd be happy to answer people's questions about that if you have more. So here's our funding disclaimer, again, related to NSF and USD and IFA. I also want to acknowledge my collaborators, Nick Brozovic and Trenton Franz, both faculty members here at UNL who are co-PIs on the current IU's grant, Diane Lally and Destiny Pettit, who are former and current graduate students on the project who were lead or co-authors on many of the publications that we mentioned before. And also Holly White, who's a new master's student that has been contributing to the course and will be doing research of her own moving forward. So with that, thank you, and I appreciate everyone jumping into the webinar today, and I hope we'll have time for questions.
Great, Cory, thank you so much. It doesn't look like we have any questions that have come through yet, so I encourage everyone out there, if you've got questions, please type them into the questions box. Okay, so it looks like we've got one coming through. It says, is WBM available on the web?
It is. It's on a very limited capacity server at the moment because we've really only used it in the course. But yeah, if somebody's interested in checking it out, I'd be happy to share that link.
And Ainsley, this is Imad. Somehow I cannot type a question. Can I just speak it?
Oh, sure. Yeah, go ahead.
Yeah, Cory, can you speak to, and you may have already touched on that a little bit, but like the challenges that you encountered from the student perspective and also from the instructor's perspective?
Yeah, so I know, so there's a couple main challenges that I think we've continued to wrestle with. One of them was, part of our motivation for moving to more of a hybrid version of the course. Obviously students tend to not get as excited about, traditional sort of course formats. And, we felt like that given the feedback we were getting from students, that trying to move to a more engaging kind of active learning approach would be, better and more beneficial for the students. So that was partially in response to student feedback from the first offering of the course. And in all honesty, I mean, students really benefit from working directly with these models and collaborating with their peers to do so and discussing a lot of these issues. I mean, the way our course is set up and designed, it just isn't aligned with that traditional lecture model of what we do. So one of the big challenges with that has been finding a classroom space that actually enables that kind of instruction. We've had access to a couple different classrooms that are, set up for very traditional, course kinds of formats. And we're actually really excited this year for the first time we have access to a room that, has capacity for our class, but has small group tables and TV screens and monitors around the room. It's not really set up for kind of a central lecture style format. So that's been one. Another one has been trying to, I think, calibrate the expectations of these different student groups. So particularly in the first year, we had a really wide range of students in terms of their place in their programs and how much background they had in water science. So, for some of them, some of the things we were doing in the class they felt like was fairly elementary and wasn't really pushing them. While, some of the students that had very little background in STEM or the water science specifically, there was a learning curve for them, and it takes them extra time to sort of get used to using the models and doing some of the things that we're doing in the course. So when you have an interdisciplinary course like this that's meant to serve a broad population of students, it can be challenging to figure out what the needs of all those different diverse student groups are and try to meet them.
Great, thank you. Do we have any other questions? All right, doesn't look like we have any other questions coming through. So I'll go ahead and move on with some CUAHSI-related things. So these are just a few upcoming events and deadlines we have. So the first thing we want to talk about is the deadline to submit 2020 CUAHSI virtual university instructor applications. So these are due by November 1st for fall 2020 participation, and you all can find more information about the virtual university and eligibility on our website. Secondly, we have a cyber seminar coming up on November 7th featuring Seth Siegel. This seminar will explore how America's drinking water became contaminated and how it impacts public health and what solutions that exist that can make U.S. drinking water safer. So registration for this cyber seminar is free, and you can register for this on our website by navigating to the Cyber Seminars tab and then clicking down onto the Troubled Water link. And lastly, there is a free workshop taking place before the AWRA conference. The workshop is on November 3rd from 1 to 5 p.m. and you all can find more information about this workshop on CUAHSI social media and our website. So with that, we want to thank everyone for joining us today, and we hope that you join us next week to talk, where we will be joined by Imad Habib, Melissa Gallagher, David Tarbotten, and Dan Ames, who will talk about collaborative development and sharing of learning resources in hydrology and water resources with focus on experiences from the HydroLearn project. So thanks again, everyone, and we hope to see you all next week.